Welcome to Plutus. Today we are covering nucleophilic substitution reactions in case of heteroaromatic compounds. So, what are heteroaromatic compounds? Heteroaromatic compounds are all those compounds which have similar structure to benzene, but they contains a heteroatom which is other than carbon. For example, pyridine, pyrols, furan, thiophenes. These are some of the most commonly known heteroaromatic compounds. Now, in all of these compounds, one thing is common that they all contains pi electron cloud, which is negatively charged and delocalized over the entire system. So first thing, in order for any nucleophile to attack it, the problem is all of them have negative charge density, which do not favors the attack of nucleophile. Specifically, if I go for benzene, since benzene is a perfectly aromatic compound, that means its electron density is perfectly symmetrical over the ring. But in case of heteroaromatic compound, for example, pyridine, if I talk about, since nitrogen is more electronegative, this electron cloud is more localized over nitrogen. So that means there is a density. There is a vacant space, whereas there is less amount of negative charge density, which any nucleophile can easily attack. So, compared to benzene, all heteroaromatic compounds are active for your nucleophilic substitution reaction, or they easily undergo nucleophilic substitution compared to benzene. Specifically talking about, let's say if I want to add a nucleophile in case of pyridine. So, my pyridine contains a given number of side 1, 2, 3, 4. So, which of the following side will be best available? So, first thing we have already seen, because of highly electronegative nitrogen, there is a vacant space on position number 4. So, ideally, everyone should expect that position number 4 is the most probable position for attack of nucleophile. But in reality, if I look for pyridine like this, and if I try to make a resonating structure for it, so for resonating structure, it will need to pull the electron density from the benzene ring, from the ring, making itself negatively charged, creating a positive vacant site for a nucleophile to approach. Then moving on further, this pi bond will move to stabilize the carbocation and delocalization of the positive charge will take place. So here, these are the following resonating structures that we will get for our pyridine. Now, for anyone looking at it, they will find that position number 4 is most ideal. But if you closely look at it, the negative charge is on nitrogen. And nitrogen is very electronegative. Now, since it is an electronegative atom, it will pull electron density from the closest position, but since it do not have any vacant d orbital, it can only apply minus I effect. So for the minus I effect, if you will find that this position is very far away, so the positive charge shouldn't be here, it should actually be here. Now the positive charge at this position is very far away, so the inductive effect is very less on the fourth position, and the positive charge which are lying adjacent to the nitrogen because of the minus I effect are the most reactive. They are the most reactive. So in terms of preferentiality, position number 2 is more reactive compared to position number 4. So any nucleophile that you are adding, it will preferentially attack position number 2 rather than position number 4. In case you want a position 4 substituted product, you first need to block the ortho sites. Now, what about in terms of position 3? Which one will be preferred? So, in order for the preferentiality, we can look for different resonating diagrams. So, first is if the reaction attacks takes place at position number 2. At position number 2, we'll find that when the nucleophile gets attached to this position, the negative charge will shift to this side and then to the other side and to the other side. In all the resonating forms, you will find that the negative charge is present on the carbon, and in only one case the negative charge is residing on nitrogen. When this attacks shift to position number 3, the negative charge entirely remains on the negative charged carbon, and there is no negative charge on nitrogen. And similarly, similar to the case number 4, when attacks takes place at position number 4, we have resonating forms which are having negative charge localized on the nitrogen. So clearly we will find that the attack at position number 3 is very unfavorable, because as for the rule of resonance, the negative charge is only stabilized on the highly electronegative element, which is only we are getting in case of at position number 2 and then at the position number 4. So that means in case of nucleophilic substitution, there will never ever be any attack on position number 3. But if you want to add an electrophile, since electrophile require electron density, in that case attack on site number 3 would be the most preferred one. Now, similar to other compounds, if you look at, for example, taking pyrrole and all other compounds which are similar to pyrrole like thiophene and furan, they will also give similar reactions. So this is what I'm taking. Positions, position number 1, position number 2, position number 3. If I want to add a nucleophile, the problem is it has a smaller ring size, so it has less tendency to show nucleophilic substitution reactions. So in these cases, you can only take the reaction in terms of only electrophiles. So for any electrophile to be here, again I have option for 2 position, which is position number 2 and again at position number 3. If electrophile gets attached at position number 2, this will be positive charge, electrophile would be here, stabilized by the negative charge, lone pair here. Now, at this position, if I take, this will be a positive charge, hydrogen here, lone pair will shift to stabilize it. So from the given resonating forms, you can clearly see since the positive charge is residing on nitrogen, that means the attack on position number 3 in case of pyrrole is not favored. So in case of pyrrole, thiophene and furan, all the electrophile will get preferentially attack positions at position number 2. Okay. I hope this would have cleared all your doubts regarding the nucleophilic and electrophilic substitution reactions of heteroaromatic compounds and how you can decide which site needs to be preferentially attacked. Okay. In case of any other doubt, you can add it to the comment section and we'll get back to you. Or is there any specific topic if you want us to make the video, you can also add it to the comment section. Thank you for joining us for today.